Hello and welcome to the second example. In the second example, we're going to talk a little bit about half-life and radioactive decay. So, of course, I'm sure you all know that in physics, the half-life is a measure of the stability of a radioactive substance. The half-life is the time it takes for one half of the atoms in an initial amount A sub 0 to disintegrate or transmute into the atoms of another element. So we're going to find the half-life of whatever substance that we're dealing with in example 3. But we're going to start with radioactive decay in example 2. So, for 6, initially 100 milligrams of a radioactive substance was present. After 6 hours, the mass had decreased by 3%. If the rate of decay is proportional to the amount of substance present at time t, then we want to find the amount remaining after 24 hours. So from right here, if the rate of decay is proportional to the amount of the substance present at time t, that gives us our differential equation. So again, dA over dt is equal to Ka, which of course is going to be a separable differential equation. So what we're going to do is we're going to solve for the initial equation. So we're going to get all of our a's on the same side and all of our t's on the same side. Then we're going to integrate the left and the right side. The left side, we're just going to get natural log of a. On the right side, we're going to get kt plus c. Go ahead and plug in our e's to both sides. We're going to get a is equal to c e to the kt, where a is the total amount of our substance and c is the initial amount. So we'll go ahead and break this up to a is equal to, or we'll say a of t is equal to a sub 0 e to the kt. And so this is our solution to our differential equation. This is how we're going to find total amount. Now, we're said that initially we have 100 milligrams of a radioactive substance. So that's our A sub 0. And after 6 hours, the mass had decreased by 3%. So then what we can write is this. We can say A of 6. So after 6 hours, it's an ugly 6. After 6 hours, the initial amount we had was 100 milligrams. E to the k times 6, so that's our t. And that's equal to just 3%. Well, 3% of 100 is going to be 97. So we're going to go ahead and solve for k so that we can find our decay constant. And we divide both sides by 100. So let's go ahead and do that. We have e to the 6. K is equal to 97 over 100. 9 better. And then we're going to put a natural log in for both sides. I don't need to show that. Y'all should know that that's where this is coming from. So 6k is equal to natural log of 0.97. And then we divide both sides by 6. So we found our k, which is going to be 1/6. Natural log of 0.97. All right, so now that we found our k, we're able to find, okay, what's the total amount present remaining after 24 hours. So go ahead and plug this into, let me box this up so that we know that, okay, now we have all of our values. And so we want to find A of 24, and that's equal to, and then we plug into our formula, so our initial amount's 100, e to our now k, which is going to be 1/6, natural log of 0.97, times our t, let me make sure I put that there, times our t, which is going to be 24 hours. Plug that into your graphing calculator, we get 88.5 milligrams remaining. Milligrams coming from right Alright, that's it. We are finished with example 6. Now, this next one says determine the half-life of the radioactive substance described in problem 7. No, it means this described in problem 6. So we'll just change that to problem 6. Alright, so the half-life is, again, their total amount being half remaining. So what we're going to do is we're going to use our equation. So if our total amount equation is really 100 e to the 1/6 natural log of 0.97 times t, then all we need to do is solve for t. So I'm hoping you're finding this section is not going to be too bad, because a lot of this you did back in pre-calc. You did back in, I guess, math analysis when you were being, well, not really introduced, but you were being reintroduced to exponentials and logarithms. So let's go ahead and solve. So if we're doing half-life, we want half the amount, so 50. That's equal to 100 e to the 1/6 natural log of 0.97. We'll put t right there and make sure that we know that that's 0.7. Alright, now solve, divide both sides by 100. We're going to get 1/2 is equal to e to the 1/6 natural log of 0.97. T, get rid of e by taking natural log to both sides. So we get natural log of 1/2 is equal to 1/6 natural log of 0.97. T, let's just go ahead and solve for t. So t is equal to 6 times natural log 1/2 divided by natural log of 0.97. And that is approximately 136.5